All right, so let's move on, and let me introduce Jan Maas from ISTA, who is so kind to give the Laudatio for Martin Heyer. So may I ask you to come to the podium? Jan has obtained his PhD from the TU Delft, and then has done postdocs. Now I have to ask you.
Warwick was the first.
Sorry?
Warwick was the first one, and then
Warwick, of
yeah.
course. The postdocs at Warwick. He has obtained an ERC starting grant, and with that grant, I think he moved to IST Austria. Or maybe it was the other way around. I apologize. In any case, Jan came to Austria in 2010, moved up the ranks, and in 2020 he was promoted to full professor at IST. He's also the organizer of EASY activities. We are thankful for that. And now we will hear the Laudatio for Martin Heyer. Please.
Okay, thank you very much, and good afternoon. So it's a great pleasure and a great honor to give this Laudatio for Martin Heyer, celebrating his great mathematical works. So as you all know, since you're here, Martin Heyer has been awarded the AZ Medal 2022 for his groundbreaking work on stochastic partial differential equations. And I would like to give you at least some sort of a small glimpse into his research and the mathematics that he has been developing. But let me start at the beginning. So Martin was born in Geneva. I mean, he is Austrian and actually spent only a few years of his life in Austria. But those were the first few years, so perhaps they were particularly important for his development. So Martin grew up in Geneva, where he went to school. As a kid, he was very much fascinated by programming. At the age of 12, he got a programmable calculator, which got him hooked into this direction. At the age of 14, he was writing computer programs solving ordinary differential equations, and already as a child he won various programming awards at competitions. Let me in particular mention that in one of these competitions he developed an audio editor, so a computer program for editing audio files. Starting, I mean, he did this as a high school kid, but he is actually has been developing this program all along, and now it's sort of used worldwide by professionals around the world, and he is actually still maintaining and developing this program as a side activity next to his mathematics. Okay, so Martin actually then, after school, moved on to study at the University of Geneva. He studied physics, kind of picking up mathematics along the way, one could say. Then in 2001, he got his PhD degree also from the University of Geneva in physics, with working with Jean-Pierre Ekman. After his PhD, he moved to the UK, where he has been spending many years, first at the University of Warwick, starting as a postdoc and then sort of joining the faculty. Then in 2009, he moved to NYU at the Coherent Institute. He returned to Warwick a year later. And in 2016, he moved to the Imperial College London. And actually, just as of this week, a few days ago, he started this new position as a professor at the EPFL in Lausanne. Okay, so Martin is of course known for many important contributions. So he worked in different areas of probability and mathematical physics. So it would be foolish trying to give a full overview of his developments in the course of this short presentation. But let me just mention a few topics. So the topic of anharmonic oscillator chains, which is something that actually I think he did in his diploma thesis already and has been sort of developing also in the years following that. Then he worked on various aspects of stochastic partial differential equations, in particular multi-scale analysis, homogenization theory, also problems related to path sampling, where the idea is that you want to sort of construct solutions to ordinary differential equations by some sort of a Markov chain Monte Carlo procedure, and the object that you end up working with are stochastic partial differential equations, and this is a direction that actually led him also to his later work on singular stochastic partial differential equations. And maybe the most, or one of the works for which Martin was most known for in the earlier stages of his career was his work on the stochastic Navier-Stokes equations, which was a very active and important subject. And one of his great achievements there is that he proved the ergodicity for two-dimensional stochastic Navier-Stokes equations driven by very degenerate noise, and solving sort of a long-standing open problem in that field. And then in the last 10 years or so, Martin has been developing his theory of singular stochastic partial differential equations, about which we already heard two talks today. And this is kind of the topic for which he has been awarded this AZ medal today. So I would like to give you maybe a glimpse into this last direction of Martin's work in sort of as elementary way as I can do. And of course, I will be very impressionistic and hand waving. So what is the idea? So as we have seen already in the previous lectures, we're interested in stochastic partial differential equations. And a sort of simple example which plays an important role is the stochastic heat equation. And let's just formulate it in one dimension. It's this heat equation driven by a noise term, which I denoted by psi. And of course, one can consider many different types of noise, but the particularly sort of natural choice of the noise is to take space-time wide noise, which sort of intuitively speaking corresponds to putting like independent Gaussian random variables at every point of space and time. So in a formal way, these are described by this covariance structure where you have these delta correlations both in time and space. Okay, so now this, of course, since these are all independent, this creates a lot of irregularity. And of course, this object does not really make sense in any pointwise sense. So in a way, it oscillates between plus and minus infinity everywhere. But it's perfectly well defined as a random distribution, in the sense that you can integrate it against smooth test functions. And now you see that if you look at the stochastic partial differential equation, there's of course some sort of a competition between those two terms. So the Laplacian is making your solution very smooth, but this noise term is actually very irregular. Yeah, and sort of the net effect of these two terms is that if you ask yourself what is the spatial regularity of this stochastic heat equation, is that for a fixed time, if you look at it as a function of your spatial variable, it will be Hölder continuous with exponent alpha up to alpha equal to a half. And so it is continuous. It's not differentiable, but you can quantify the Hölder regularity precisely. Of course, Hölder regularity means that you can control increments of a function in terms of a constant times the distance between x and y to the power alpha. Okay, so roughly speaking, that means that as a function of space, the solution is going to look like a Brownian motion. And therefore, it's highly non-trivial if you would like to consider sort of nonlinear versions of the stochastic heat equation. And it was a big open problem for decades to make sense of equations of this type with derivatives appearing in the nonlinearities. And we have already seen sort of a prime example of this situation is the so-called KPZ, Kardab-Perez-Zhang equation, which arises in the theory of interface growth, where you have the the square of the derivative showing up. And of course, the derivative is, I mean, the solution is supposed to be the Hölder continuous of exponent roughly 1/2. If you differentiate it, you lose 1 degree of regularity. So of course, this square is something which you're not allowed to do. Okay, so that's the problem, and of course, this is not sort of one particular equation, but there is a whole class of important PDEs or stochastic PDEs arising in physics, which have similar features. So the KPZ equation is arising in interface evolution equations. There's this parabolic Anderson model, which describes sort of weakly killed diffusions, which is given by sort of this heat equation with this product of the solution and the noise. And if you want to study this in 2 dimensions, you have a problem making sense of this expression. And another prime example is what we have seen in Hendrik's talk, this dynamical 5-4-3 equation, which describes phase coexistence near criticality. And in 3 dimensions, this equation is also very much ill-posed. So the big problem in all these equations is that the nonlinearities are ill-defined. And well, it used to be a big open problem, giving any sort of rigorous mathematical meaning to these objects. So the breakthrough work of Martin Heyer is actually that he developed a solution theory for these equations, and actually not only these 3, but really a robust solution theory which applies to a wide class of singular stochastic PDEs, and which comes actually with very nice continuity properties. Okay, so yeah, so his breakthrough is actually contained or maybe summarized in if you try to give a theorem, it's maybe this statement saying that every semilinear stochastic partial differential equation that is subcritical has a unique local solution modulo renormalization. So I will try to say some more words about this. What it means by subcriticality is roughly speaking that if you zoom into your equation, so you look at it at very small scales, then sort of the strength of the noise is somewhat stronger than the nonlinearity. And so that's what I mean by subcriticality. And it's this theory that Martin developed is contained in a series of four papers, which are starting from this theory of regularity structures from 2014 that Martin developed, and then the sort of 3 papers further completing this theory with co-authors Brunet, Zambotti, Chandra, and Chevirev. And this has been developed in the past few years, and of course, the end result is a very massive amount of mathematics, 561 pages if I did the computation correctly. But of course, what's more impressive is actually the sort of the innovation contained here and sort of the complete novelty of the mathematical methods that Martin developed, which really pushed the theory further by really enormous amount. Okay, so I will do this into this theory in this short presentation, and I would like to do this maybe in sort of with the least amount of technicalities. And to do that, I would actually like to present some of these ideas in the simplest possible context, which is the context of stochastic ordinary differential equations, which is of course much simpler. But some of the philosophy of Martin's work can be sort of understood already in this elementary situation. So let's look at stochastic ordinary differential equations. So you look at a differential equation driven by a vector field A, and here's a sort of a noise term. So you have a vector field B, and you apply your solution and multiply this with white noise. So now just in time, because there's no space. This is just ordinary differential equations. Now, or if you write it in the way that mathematicians usually write it, it looks like this: a stochastic differential equation with a drift and a noise term. And of course, also in this very much simpler context, the issue is you need to make sense of what it actually means. You know, this expression appearing here. So you need to make sense of the integral of a function of your solution with the Brownian motion. Yeah. And well, why is this non-trivial? Well, what you need to do is you need to make sense of integrals of a function f against the function g. And let's look at it very deterministically. So if you have a function which is continuous, f and g is actually continuously differentiable, then it's of course easy, right? So you can just define your integral like this. Yeah. If the regularity is sort of the other way around, if f is in C1 and g is just continuous, it's also easy, right? Because you can integrate by parts, and then you're back to this previous situation. And sort of the natural thing is then to ask, can you actually interpolate between these bounds? So can you sort of trade regularity between f and g? And that's exactly the content of the theory of Young integration, which goes back to the 1930s. And sort of the upshot of this theory is that these kind of integrals of f against g, they are actually well defined, even if your functions are just whole or continuous. But what you need is that the sum of the exponents is actually bigger than 1. Yeah, so that interpolates between these two statements. And the fact is that this is actually sharp in the sense that you cannot construct this integral in a continuous way if you do not have this assumption on the exponents. But of course, this is a problem for stochastics, because if you want to solve SDEs, then you actually require alpha and beta to be less than 1/2. It would be the situation here, where your Brownian motion is Hölder regularity less than 1/2, and the same is true for this guy. Okay, so of course, the way out is you need to use some probability. The regularity by itself is not sufficient. And that's the context of the very classical stochastic integration theory by Ito from the 1940s. And this exactly gives a meaning sort of to these integrals that you need. But the point here is that this is really a probabilistic theory, right? So that you cannot do this is really in a pathwise sense. So you really make use of probabilistic concepts, so like martingales, filtrations, and the crucial bound is then an isometry in L2 over the probability space. Yeah, this famous Ito isometry, which allows you to make sense of stochastic integrals as random variables. So this is, of course, a very beautiful and a very powerful theory with many applications, but it's not at all well suited to treat stochastic partial differential equations, where the problem is that you have this roughness in space. And the thing is that if you have these stochastic integrals, it really relies somehow on the fact that things are one-dimensional. But even more, you really need some sort of an arrow of time, some sort of a flow of information to make sense of these stochastic integrals. And the other thing is that which is sort of less attractive about this theory is that there is no continuous dependence in a pathwise sense of the solution on the driving noise W. Okay, but there is actually a way to make things work in a more pathwise sense, and this is the theory of rough paths, which has been developed by Lyons in the end of the 90s, and it can be seen as a precursor of Martin's theory of regularity structures. So the idea is here that if you have a Hölder continuous function and a smooth vector field, if you want to solve this rough differential equation, well, you run into the problem that these integrals are ill-defined. Yeah, but the philosophy is now the following. So what you do is actually, instead of trying to make sense of these integrals for arbitrary functions, what you do is first you postulate the value of your integral, in a special case where you just integrate x against x. And so that's sort of the simplest integral that you cannot make sense of. And what you do is you postulate. So if you apply this to stochastic problems, is that what it means is that you can actually give a meaning to this integral sort of by hand, right? And in applications to stochastic differential equations, you can do this. So since in particular, these are often like Gaussian processes for which you can use specific probabilistic techniques. But then the point is that if you now assume that sort of you have a function y which is controlled by x, in the sense that increments of y can be controlled in terms of increments by x, then the thing is that you can actually make sense of the integral of y against x in sort of a consistent way. Yeah, and this relies on the usual kind of Taylor or Riemann sum approximation. But the thing is that you use this information, this extra information coming from these the integral of x against x. And then you can actually solve your ordinary differential equations in the space of rough paths. So this sort of presents a different point of view on stochastic differential equations, where the idea is that if you want to solve your stochastic differential equations, what you do is you start with the noise, then sort of you enhance it in a certain way. And what it means is that you actually give a meaning to the integral of the noise against itself. And then the point is that there is actually a completely deterministic solution map, mapping the noise onto a solution to your ODE. And so this is sort of a more pathwise way to look at stochastic differential equations, and it can be seen as a very special case of Martin's theory. Okay, so let me try to say a few words about Martin's theory of regularity structures, which pushes these ideas much further. And what it involves is actually, it involves a completely rethinking about the notion of regularity. So what does it mean, regularity, in this context? Well, the classical way of measuring regularity is actually that you try to measure how well a function can be approximated by polynomials. And so that the differentiable functions approximated by linear functions locally. And Holder continuity, for instance, quantifies how good this approximation is. So Heiler had the bold idea of actually pushing this idea much further. So what he proposes is actually to replace these monomials, which you use to measure regularity, by completely different objects, which can be very singular. And they are chosen in a clever way, depending on the problem that you want to solve. So what you do is you replace these monomials by what he calls a model. And these are just a finite set of random, well, possibly random distributions, which are used in a clever way, and what you want to use to sort of locally describe the solution of your problem. And so, for instance, in the example of the KPZ equation, what these functions are, they're actually often sort of depicted by these graphical symbols, but they are sort of explicit distributions which you build from the noise and the heat kernel, and by multiplying these objects with each other. Okay, so that's in some sense analogous to this enhancement step that we saw in the setting of ODEs. And then sort of the next idea is that actually you do not do your analysis with sort of classical objects as we all learn to do, but Martin sort of developed a whole kind of universe, a whole space of what he calls model distributions. And what these are functions defined on your space, which assign locally to every point in your space sort of a generalized Taylor series coefficient. So you assign coefficients to each of these irregular objects. So the idea is that sort of locally you describe how your sort of very singular distribution might look like in terms of these fixed model that you chose. And now the amazing thing is that you can actually develop a whole analysis, at the level of these modeled distributions, where sort of classical operations have a counterpart. So you can multiply these objects according to certain rules. If you can sort of make sense of composition of smooth functions, you can make sense of integration, and you can set up a whole analysis. And sort of intuitively speaking, the fact is that very singular distributions, which arise sort of in the description of your equation that you're interested in a way they behave if they were smooth, but not smooth in a classical sense, but smooth in this in the sense that you can approximate them in terms of these very singular objects. Now, this is all very general, sort of high-level framework, but the key point of Martin's theory is that there is a reconstruction theorem, And this reconstruction theorem tells you that you can actually identify these abstract expansions under certain conditions uniquely with sort of real classical distributions as we know them. So you can actually go back to sort of the real world and obtain sort of solutions to real equations. So schematically, this gives us the following picture. So how does Martin solve singular SPDEs? So the first step is what you do is you take your singular equation, you regularize the noise at some scale epsilon. Then starting from this noise, what you do is you build this canonical model. So finitely many objects which you construct using the noise and which are supposed to describe objects that you're interested in sort of locally. And then using sort of the analysis that Martin developed, you actually solve your abstract stochastic partial differential equation, in the space of model distributions. And at the end of the day, you apply this reconstruction map to obtain a real distribution. And so that's schematically depicted here. So here you start with the regularized noise, you lift it to this abstract space, where you can actually solve the equation, and then you reconstruct it. And now the thing is that, of course, this map is actually very much not continuous because we don't expect it to be continuous. But the thing is that actually these objects, so the solution map here and the reconstruction operator are actually continuous. So actually all the sort of discontinuity is really contained in this step, which is the construction of the model. And also these parts are completely deterministic. So it sort of cleanly separates the randomness and the deterministic part of the problem. Okay, now the major problem which arises in this construction is that, of course, what you would like to do is you would like to send epsilon to 0 to obtain a solution to the original equation. But the point is that if you do that, then this kind of canonical model that Martin defines does not in general converge to as epsilon tends to 0. So what you need to do, and what Martin did, is actually you need to develop a renormalization theory that applies to this framework. And that's sort of schematically, it's the following idea. And of course, I mean, this looks very simple in these one sentences, but there's a extremely sophisticated theory behind this. But the idea is that you would like to modify your canonical model to obtain a renormalized model. And of course, this has to satisfy certain conditions respecting symmetry of your problem. And the point is that you want to do it in such a way that actually these renormalized models, they converge to a limit in probability. And the amazing thing is that Martin showed that this can be done. And it can actually be done in a systematic way for a whole class of equations. And then the next step is actually that you can actually identify these renormalized equations. You can identify this with sort of modified equations at sort of the base level. And so what you obtain using this construction is you obtain a renormalized solution. And the way how you get is really using Martin's theory. So what you do is you start with your the limits of these renormalized models. So it's this X hat. Then you apply this abstract solution map, and then you apply this reconstruction operator. And so these gives you continuous maps, and this defines a notion of renormalized solutions to this stochastic partial differential equation. And of course, what's built into this construction is that you actually also get convergence of sort of renormalized approximations to the equation. So schematically, the picture is as follows. So here's the same sort of solution construction that we saw on the previous slide. The thing is now that what you need to do is you need to apply this renormalization operator here at the level of your model. And then what you can in fact do is that this operation of renormalization at this abstract level, it actually corresponds to something also at the level of your real equation. And so what I added into this picture is this n. So this is the nonlinearity of your equation, because obviously your solution is going to depend on the nonlinearity. And so doing this renormalization here at the level of the model actually corresponds to modifying the nonlinearity of your equation. And so for instance, in the example of this KPZ equation, what you get if you do Martin's construction is that if you consider this modified KPZ equation and you renormalize it, it actually corresponds to changing the nonlinearity by sort of subtracting a constant depending on epsilon. And this epsilon is or the C epsilon is of course something diverging. So it's something of the order 1 over epsilon. And then the statement is that these renormalized equations actually converts to this non-trivial limiting object, which is the renormalized solution that Martin constructed. Okay, so of course this is very impressionistic, but to summarize, what Martin developed is a very sort of robust solution theory, which really applies to a large class of equations, and it really gives sort of a fully sort of automatic way to solve these equations. And one of the kind of more recent highlights of this theory is also that he made sense of this sort of what's called the geometric stochastic heat equation, which can be seen as sort of a canonical random motion in the space of loops on a Riemannian manifold. And this is an example of a very singular equation. And here's just to illustrate a little bit the sort of the complexity of what's going on. Is these are sort of the model that you need to make sense of these equations. So you see that there are really many terms. And if you would try to make sense of this by hand, that would be clearly something that would be very unpleasant and if at all possible. And Martin's theory gives really a fully automatic way to deal with these very singular objects and to make sense of these fixed points arguments in these abstract spaces to obtain real solutions to your equations. So this theory really obtains or really led to very impressive, spectacular results, and clearly there's great potential for many further breakthroughs and further exciting developments. So with this, I would like to close and congratulate Martin on this AC medal.